All right, so previously we talked about measuring an analog voltage using the voltage probes, and then watching how we can select the voltage divider ratio, and seeing how the signals are operated on and then outputted to the microcontroller to be displayed. But that was for analog voltages. The oscilloscope can also read digital voltages. So by digital signals, we mean zeros and ones can be represented by square waves, where we have a high voltage and a low voltage representing a 1 or a 0. So if we look at this waveform generator, I have it set to produce a square wave with plus 20, minus 20, which is a very high amplitude square wave. And we're going to say that this plus 20 represents a 1 and this minus 20 represents a 0. The frequency of this square wave is 5K. So once the signal goes into the input has a 10K resistor and a Zener diode right here. This Zener diode has a breakdown voltage of 12 volts, which limits the voltage here to 12 volts. And that's because we don't want a voltage too large inputted into this chip, otherwise it could damage the chip. So this will limit to 12 volts, which is the system voltage here, plus minus 12. So that's fine. So once we have that voltage, this voltage will then go into this LM339. This LM339 is a comparator chip. I'll take the voltage here and compare it with the voltage at pin 2. Pin 2 has a reference voltage of 1.65 volts as a constant. This voltage is obtained by going to the power supply system and tapping off 1.65 volts from the 12-volt power supply by using a voltage divider as seen here. And so if the system is greater than 1.65 volts, this will bring this output down here and produce a high output of 3.3 volts. If 1.65 volts is larger, then this system will be grounded in here and the output will be around 0 volts. So over here we have 3.3 volts, which we have used as our high voltage, or as a voltage of 1. We use 3.3 volts because 3.3 is a standard TTL digital logic voltage. And so in order to generate 3.3 volts, so we go back to our power system here, and we just need to tap off 3.3 volts using this resistor and then this voltage divider ratio as seen here. So you need to notice that 1.65 volts here is exactly half of the high voltage. So in other words, we're comparing this voltage, and if it's at least greater than half of the high voltage, we consider it a high. And if it's less than half of the high voltage, it's considered a low or a 0. And so that's how we can translate this inputted digital signal into a 0 for low, 3.3 to high digital signal that can be read by the microcontroller. So since I set this, so now we just need to run the transient on that. So this is set for 1 millivolt. So I run that, and the output, we notice that we get around 0 as the minimum and around 3.3 as the maximum, even though the original input was plus or minus 20 volts because of all the conditioning that we performed over in here to make sure that it's now at a voltage that the microcontroller can read, because the microcontroller cannot read a voltage as high as 20 volts and cannot read negative voltages. So with that microcontroller conditioning, that digital signal can be read by the microcontroller. So in order to get it to the microcontroller, we have to first export it out as a text file. So we're going to call this digital input. Call this digital input. Let me X out the old digital input. So I'm not going to save that, so that way I can overwrite this digital input with the new digital input. All right, so now I can open that digital input file in Excel. So I open it up here, where digital input is. All right, tab delimited as normal. All right, so we still need to get this in a format that's readable by the microcontroller. So we're going to use the help of one of our macros, the CSV samples. But if we run the CSV samples, notice how this row is blank, because this row was originally the voltage divider, the voltage ratio that we needed to multiply by. But for the digital inputs, we don't need to multiply by a scaling factor or anything. So that's why this one is blank. And notice that it still says an offset of 500 millivolts, but for our input, for the digital signal, there is no offset. So I can remove these two rows like that. This top row is still 1 millivolt or 1 millisecond approximately, because this is the maximum time. We'll still need that. And then the rest of those samples are just data. So with this, I can say this as a CSV. Say this is going to be the digital input CSV. And I can save that. And now the microcontroller can read the CSV, and given the time, can calculate, given this maximum time, can calculate the number of the ones and zeros from this file.